Hello, this is Ms. Chambers, and I am going to attempt to answer the question, why do we need the tangent line? Why it's so important. So, as a straightforward answer to this, the reason for finding the tangent line at a point is the tangent line has the same slope as our function at that point. So if we have a function that's a curve, like this for example, remember the tangent line is a line that only touches the curve at one point. So if I drew an example, there would be my point, and then the tangent line would only cross or touch my curve at that one point. And it just so happens to also have the same slope as my curve at that point. So since, if we have some curve like this, it's not linear, so I can't just count rise over run to find the slope. So if I want to find the slope, I use the tangent line. Now, to introduce you to the tangent line, we're going to develop, for lack of a better word, a formula for finding the slope of the tangent line. And in order to do that, we've got to use the secant line, or the idea of the secant line. So remember, the secant line is actually a line that travels through the curve at 2 points. So I always think secant cuts through the curve. So 1 point, 2 points. And the reason why we're going to use the secant line is because we know how to find the equation of a line given 2 points. So let's do that. And we're going to use a lot of notation here in order to create a general formula. So we're going to start with notation that you're probably familiar with, and then we'll modify it so that it'll be the notation that you'll see in your textbook. So first, let's say that this point, and I'm going to do my best to write neat, this point is x1, y1, and this point is x2, y2. Okay? So if I wanted to show the slope of the secant line, I would use the slope formula, which would be y2 minus y1 over x2 minus x1, right? Okay, so that would be your slope of your secant line. Now, another way to think about it is slope is the change in the horizontal distance over the change in the, I did that backwards, the change in the vertical distance over the change in the horizontal distance. And how do we represent change in math? By using delta. So the horizontal change, got it right this time, would be delta x, and the vertical change we would consider delta y. So the other way to represent slope would be to say change in y over change in x. Okay? Well, there's another way that you're going to see in your calculus textbooks that they show this slope. And what they use is they use function notation. So we have these same points, and I'm going to take a little time to do some copying here. Copy and slide it on over here. So we're going to use our secant line that we had before, but now instead of using x1, y1, x2, y2, we're going to use function notation. There. It's ugly, but it's there. Alright, so instead of saying x1, y1, I am going to say some constant c, and then when I plug it in my function, I will get f of c. So this point is c, f of c. Here's c. Okay? And then that would mean that this point, I would then take the horizontal change, which was delta x, so it would be c plus delta x. Ooh, that's ugly. Let's rewrite that. Alright, we'll write it up here. C plus delta x, now it's big and ugly. And then my y value would be plugging this in to function notation. So f of c plus delta x. So same thing we did here, just got a lot more complicated looking. But it's not. It's not any more complicated. Because all I did was I made my x1 a c and my y1 f of c, which makes sense because we would plug the x into function notation. And then we said, well, this point, we already said the horizontal distance would be delta x. So really it's just c plus that horizontal distance, delta x. And then the only thing we did here was take our independent and plug it into the function notation. So, if I used this notation, this slope would become y2 minus y1, which is just f of c plus delta x minus f of c, over x2 minus x1, which would be x2 c plus delta x minus c. And look what happened. C minus c. So what this simplifies to is f of c plus delta x minus f of c over delta x. This is the notation you're going to see in your calculus textbook, especially when they start talking about the formal definition of a derivative. But this would be the slope of my secant line. Now think about it. If we move this point right here closer to the left point, so close that the distance between them would be 0. So think about that again. Instead of putting my second point way out here, I slide it so the distance between the 2 points would be 0. What that is the horizontal distance approaching 0. Approaching. It sounds like a limit. So basically we're saying, if I can make this approach 0, I'm going to start getting closer to the actual tangent line. And that's where the tangent line equation comes from. So let's rewrite our slope formula for secant line. So we said f of c plus delta x minus f of c over delta x. And this time, instead of saying this is the slope of the secant, let's make it the slope of the tangent. And the only thing I have to do is say, the way I get the slope of the tangent is I make this horizontal distance approach 0. So what it looks like algebraically is I say the limit is delta x approaches 0. That would be how I would find the slope of the tangent line, which is also the derivative. So now you know the formal definition of a derivative. In very ugly handwriting. Ta-da!